Okay, hello everyone. So let's continue with the lecture here. So in this part of the lecture, we are going to look at more examples on DC analysis for the MOSFET. Okay, so in particular in this part of the in this week's lecture, we are going to look at the voltage divider bias. So if you recall previously, we looked at the fixed bias, and now we're looking at the a more stable circuit, okay, which is the voltage divider bias. So what it means by the voltage divider bias is that the voltage divider bias, the main characteristics of the voltage divider bias, as you can see, is actually on the R1. So we have the R1 connected to the main source, the VDD, at one end, and the other end is connected to the gate terminal. Okay, this is your gate terminal. So if you have a resistor connecting between your main source VDD to the gate, then you can identify this circuit as the voltage divider bias. Okay, so the analysis for voltage divider bias is a little bit different. We're going to go through how we can analyze the voltage divider bias. Okay, so given the circuit below, given the circuit below, it is given that the threshold voltage VTH equals to 2 volts, K is 0.2 milliamps per voltage squared, and we want to find the Q point, the operating point, VGSQ, IDQ, VDSQ. Okay, so you want to find the three parameters there. So what's the first step? So the first step we want to do is we are doing a DC analysis, which means that we are going to remove all our capacitance, make it open circuit. Okay, open circuit on all the capacitors. Step number two, we identify is a voltage divider bias. The first step here, okay, first step is remove cap capacitor. Step number two, calculate VTH and RTH, where TH is your Thevenin, not the threshold. Okay, so VTH is the Thevenin voltage and RTH is the Thevenin resistance. So we'll see how to calculate the RTH VTH. But once you have the RTH VTH, you can then convert this into a fixed bias circuit, and we do a normal analysis like we've seen in the previous video on how to analyze fixed bias circuits. Okay, so in this case, to calculate VTH, so VTH is simply VDD, okay, VDD R2 over R1 plus R2. So it's basically a voltage divider where we are looking at the voltage across R2. Okay, we are looking at the voltage across R2, and it's given by VDD, so which is 9 volts. VDD is 9 volt. R2 over R1 plus R2, and R1 R2 is given 150, 160 kilo ohms. And your RThevenin is simply R1 parallel with R2, which is equals to R1 R2 divided by R1 plus R2. Okay, so once we have our VThevenin and the RThevenin, we convert this into a fixed bias, and after that we do a normal fixed bias circuit analysis where we derive the three equations. Okay, we derive the three equations. So if you remember, the first equation is the ID VGS characteristics. So ID is equals to K VGS minus VGS TH squared, and then we have the first equation. The second equation is the KVL loop, okay, between the gate and the source. So KVL gate source, okay, which is here. Okay, and the third one is the KVL between the drain and the source, which is right there. Okay, so once we have these three equations, we can draw the graph, the characteristic graph, ID-VGS graph, and we can calculate VDS from our IDQ. Okay, so let's have a look at the solution here. We have the solution. Okay, so the first step is remove all caps and draw the DC equivalent circuit. Step number 2, find VTH. So using the equation just now, okay, using the equation we get this is our VDD, this is our resistors, and we get our V Thevenin is equals to 4.65 volts. And then our R Thevenin is equals to 77.42 kilo ohms, which is just a parallel of R1 R2. And then what we do is our V Thevenin is here. Okay, our V Thevenin 4.65 is there. And where is our R Thevenin? So our R Thevenin is there. Okay, 77.42. Okay, so once we have our V Thevenin, our R Thevenin, now this becomes a fixed bias circuit. Okay, so it's a fixed bias circuit with the source resistor RS. Okay, so the next step, what they do here is they derive the gate to source KVL. Okay, the gate to source KVL is right here. So gate to source KVL is simply, we've done this analysis, so you can derive the equation there where VGS is equals to 4.65 minus ID1K. Remember the gate current is 0, and and the ID equals to IS. Okay, so these are our approximation. That no current goes through the gate, and our drain current is equal to the source current, and therefore we can derive that our VGS, which is between here, this is our VG, and here is our S. So VGS is given by 4.65 minus ID1K. Okay, so and remember that the gate to source loop will get our load line. Okay, we get our load line. So how to get the load line is to just set your VGS 0. So if we put our VGS here 0, then what happened to our ID? Okay, so if VGS is 0, ID is 4.65 divided by 1K, which is 4.65 milliampere. And then to get VGS at ID 0, so in this case we set ID here equals to 0, and we see what happened to our VGS. So if this is 0, then you can see clearly simply that VGS equals to 4.65 volts. Okay, so now we have our load line ready. Okay, we have our load line ready. 4.65. Okay, we have okay, so we have 4.65 there for our load line. But then how to get our IDVGS curve? Okay, so IDVGS curve, as usual, we are going to use this equation here. ID equals to K VGS minus VGS TH squared. So K is given, okay, and then our VGS TH is given, and we can create a table as we've seen in the previous lecture. So we create the table, we make the line, and we finally get our operating point. VGSQ is 3.9 volts right here, and then our IDQ is a little bit less than 1 milliamp, 0.7 milliampere. Okay, so once we have IDQ, VGSQ, we are going to take this value 0.7, and we're going to put it inside the drain to source loop KVL, and get our VDSQ. Okay. So we have an ID here, the two ID here, and we have our VDS that we want to calculate. Okay. Okay, so this is quite straightforward. Okay, quite straightforward. The only difference than before is just that we have the voltage divided bias, where you need to calculate your Thevenin voltage and Thevenin resistance. Okay, so let's look at another example here. Let's look at another example. So this is example. The difference now is we have this is still a voltage divided bias. How do we know? Again, we are looking at the R1 here. Okay, connecting between the gate and the power supply, okay, VDD. So straight away we know it's a voltage divided bias, and because it's a voltage divided bias, we need to calculate our Thevenin resistance and Thevenin voltage, okay, VTH. But you have to be careful here. Here we have a VSS minus 12, okay, VSS, minus 12 down below, and we have a plus 12 on the top, and here K is not given, okay, but it's given the VGS-TH, VGS on, ID on, and from here we've seen in the previous video that we can calculate our K is simply equals to ID on divided by VGS minus VGS-TH squared, and from there we have 0.556 milliamps over voltage squared for K. And from the K here we can have our characteristic equation. Okay, so let's see how to calculate our Thevenin. Okay, what is our Thevenin voltage and resistance? Okay, okay, so the R Thevenin is still the same. Okay, the effective resistance R Thevenin, okay, is simply R1 parallel with R2. Okay, but the V Thevenin we have to be careful. But V Thevenin is now we have 12 R2 over. Okay, here. So V Thevenin is equals to 12. Okay, R2 over R1 plus R2. Okay, plus negative 12, which is down here, negative 12. Okay, it's negative 12. Negative 12 R1, okay, we are looking at the top first, over R1 plus R2. Okay, so for a two supply voltage divided bias, our Thevenin voltage has two components. Okay, we have the top component and the down component. So if you do this calculation, okay, R1 R2 is given. So if you do this calculation, we are going to get, so you can see here is first part here, second part there, we are going to get minus 2.29 volts, and then R Thevenin is simply the parallel of R2. We are going to get 4 mega ohms. Okay, so here is our V Thevenin. Now we have a fixed bias, okay, FB, fixed bias. We have R Thevenin 4.05. We have the V Thevenin. Oh, okay. So here is negative. So there's a mistake there. So it's a negative 2.29 volts. Okay. So from here we do the same analysis as before. We're going to have our first equation here. Okay, where we use this. This is our K and VGS-TH, and we get the graph and we get the characteristic ID-VGS characteristic equation. And again, number 2, we need the KVL loop here, okay, for the load line, and for VDSQ we need the drain to source loop. Okay, so let's see how they calculate here. So here is your load line equation. Is minus 2.92 minus ID 0.75K plus 12. Okay, same analysis as before, except that we have a negative 2.92 there, plus 12, okay, there. So if you do this correctly, okay, so let's have a look here. So basically it's minus 2.29 minus IG RTH, okay, plus VGS minus IDRS plus 12 equals to 0. Okay, so this is our KVL loop. Okay, minus 229 minus plus VGS. Okay, so this is 0. Okay, IG is 0. We know that IG is 0, and sorry. This is minus VGS, not plus. So VGS is going to be equals to so we move VGS to the other side. It's going to be 12 minus 2.29 minus IDRS. Okay, so VGS is 12 minus 2.29 minus IDRS. So that's what so you get here. So 12 minus 2.29 minus IDRS. And if we set our VGS 0, we can find ID. Okay, so ID is 12.1 milliamps. And if we set our ID 0, then we can simply get VGS is 9.08 volts. And from there, you can draw a load line. Okay, I think there's a mistake here. So 9.08 is maybe around here, and then 12 is there. Okay, so our load line is actually it's actually like this. Okay, so be careful doing the load line. So I think it's a mistake there. So then we get our, it's not going to change much. So we get around 3.9 and 5.8. I think that's correct. 3.9 and 5.8. Okay, almost 6, but not 6 yet. Okay. So depending on your graph, so you get 3.9 is IDQ, 5.8 right here and right here. And once we have the IDQ, we have the drain to source loop. Okay, our drain to source loop is quite straightforward. I think we've seen already in the previous video. We put in our ID and we can calculate our VDS. Okay, so VDS is 12.49 volts, and then we can also calculate VD and VS. So VD is simply, VD is here. Okay, so VD is simply equals to VDD minus IDRD. Okay, so it's just a drop. VDD minus the drop on the RD resistance, and we get our VD. Okay, and then VS is here. VS is there, and VS we can say is simply VD minus VDS. Okay, VD minus VDS. So VD minus, here is our VDS. So VD minus VDS, we should get our VS. Okay, so here what we're doing here is VDD minus IDRD. ID is given. ID we calculated here from here. RD is given. VDD is given, so we can calculate is 3.64 volts. And for VS, VD we obtain here. Okay, VD we obtain here, and VDS we obtain from here. Okay, so this minus this, we should get 9.08 volts. Okay, so I think that's all for this part of the video. We will discuss the next example in the next video.